Here is a projectile motion problem that makes you think a little bit. We have a 6-meter tall building, 5.5 meters away from where you decide to kick a ball with a velocity of 18 meters per second, 58 degrees above the horizontal. If the building has a length of 21 meters, where will the ball land? Let's start off by drawing this out. We've got our ball. It's 6.00 meters to the top of this building. And we've got 5.5 meters away. And this thing is shot at 58 degrees above the horizontal. And I'm going to assume that this ball is going to go over the wall and land somewhere over here, but it could also have hit the wall, so we need to make sure that it doesn't hit the wall. And then we're also going to think about, depending on how long this building is, if it's going to hit the top of the building or it's going to overshoot the building. I'm going to leave my picture like this for now. Here's my max height. We'll call that point C, because I'm also going to consider this point B here, the point where it reaches the wall. And there's going to be this point D, where it may hit the top of the building, or it may also get to point E where it hits the ground. So we'll see what happens there. Let's get a reference frame going, X and Y. Because I'm going to try and change this two-dimensional problem into one-dimensional by decomposing my first vector A into its components. All right, as usual, we have our velocity of 18 meters per second times cosine of our angle 58 degrees. We'll get that number, and we'll also get our y component, taking our velocity times sine of our angle. Do that in the calculator. Now what I want to do is check to see if this ball will make it over the wall or hit it. What I'm going to do is use my x component to figure out the time for it to reach the wall, and then I'll use that time to figure out what height I'm going to be. Will I hit the wall or get above it? All right, so let's use the x direction first. There's only one equation for the x direction. Use this one. It's for a constant velocity because the object's not accelerating left to right. Put in your x component of your velocity and this displacement to solve for time. We get a time of 0.58 seconds. We're going to use this time in the y direction to figure out how high it's going to be. This equation is good because it uses the initial velocity, which we know, the time that we now know, and the acceleration due to gravity to find the displacement in the y direction. We get 7.20 meters, which is greater than the height of the building of 6.00 meters, therefore clearing the building. So we will actually be in fact clearing it by about 1.2 meters, flying up to a maximum height and coming down. The next question is, will I land on top of the building, or am I going to overshoot it and land on the ground? There are two ways we can figure this out. We can use a horizontal direction and know the building is going to be 21 meters long. And we'll figure out how much time for it to go, 21 plus 5.5 meters in the horizontal direction, and figure out in that time what height we're going to be at. Or we can figure out the times at which the ball is at 6 meters high and figure out how far it will have traveled in that much time. In both approaches, we'll be using this equation and this equation. This equation is easier to solve than this equation for time, so I'd recommend using this one. Regardless though, if you found this time using this equation, it gives you the same answer overall. All right, I've written this equation here. I'm going to substitute in my horizontal displacement from A to D. So it's going to be 5.5 plus 21 meters. Notice I used the 9.54 meters per second, which is the x component of my initial velocity, which doesn't change during the trajectory of the motion. We get 2.78 seconds for the ball to travel this 5.5 plus 21 meters to the right. Let's figure out how high we are in the air. This vertical displacement is 4.51 meters, which is less than the height of my building of 6.00 meters. This tells us that the ball is already going to be down here when it travels this distance, so it does mean that it does in fact land on top of the building. So we now know that it does not overshoot the building. We know it lands on top. Let's state by how much. Now I'm going to need to solve for time using this equation. Given the vertical displacement and the initial vertical velocity and the acceleration, I can now find the time when it's at a height of 6 meters. That's the height where it's going to hit the building. And there's going to be two times. There's going to be a time where it's telling me on the way up it's at 6 meters, right about here. And then the time here from going all the way up and back down, that's my second time to get to here. Notice I put my vertical displacement at 6 meters, which is the height of the building. This is my initial velocity in the y direction, and here's my acceleration due to gravity. And now it's a matter of solving this quadratic. All right, so using the quadratic formula, we end up getting delta t is equal to 0.462, and .649 seconds. As I was saying previously, this first time is a time for it to go from A to B on the way up. That's the 0.462 seconds. The second time of 2.649 seconds is a time to go from A all the way up and down to D. So we are going to choose the 2.649 seconds and put that into the horizontal direction to figure out how far I've traveled to the right. All right, so we put in our 9.54, which is our x component of our velocity, and our time, as discussed, and we end up getting 25.27 meters. So now we need to choose what our reference point is going to be for our distance when we're trying to answer by how much did the ball land on top of the building. So let's choose the front wall. We found 25.27 meters to be from A to D in the horizontal direction. So now we need to figure out, well, how far from this front wall we're going to get. So why not go 25.27 minus this 5.5 piece to get this distance from front wall to D. Important now to make our conclusion. We find that therefore the ball will land on top of the wall, on top of the building, (19.77 meters from the front wall. Great, we got it, done.